Gauss's law, Resnick Halliday, the electric field due to a long conducting cylinder. So in this problem, we have a cylinder, an inner cylinder, which is carrying a charge plus Q, and this is conducting in nature. And there is outer thin cylindrical envelope, or you can say cylindrical shell, with a charge of minus 2Q. And you are being told using Gauss's law, find the electric field at all the points outside the conducting shell, the distribution of the charge on the conducting shell, and the electric field in the region between the cylinder. Now see, here one word is given, very long conducting cylinder. So we will have a model of infinite cylinder. We know when we have infinite line or infinite cylindrical charge distribution. So already we know when we have the infinite cylindrical charge distribution, we can ignore the edge effects and the field will be having cylindrical symmetry. Remember, field in this case has a cylindrical symmetry. The field is perpendicular to the curved surface everywhere and has the same magnitude over any given curved surface. This is for infinite model. Already we have seen all this in fundamental, where we have cylindrical symmetry. Here though, precisely in this problem, the cylindrical objects and surfaces are not infinite in nature, but it is given a very long conducting cylinder. And Gauss's law can be applied for finding the electric field. The system has certain symmetry. So we will assume as a very long conducting cylinder to have the cylindrical symmetry. We will approximate it with the infinite model of the cylinder and apply Gauss's law to find the field. So basically there is one inner cylinder, a conducting inner cylinder, okay? So if I'm making the inner conducting cylinder, something like this, of length L, and it has a total charge of plus Q. And then I have an outer same length, it is very thin envelope, that is called a cylindrical shell with a charge of how much? Minus 2Q, correct? And this is the common axis. So this is, both are coaxial. So this is common axis. And as I told you, by the nature of the length, as it is giving very long, we will assume the model of cylindrical symmetry, no fringing effect. So the field would be going like this. Field will have cylindrical symmetry. Everywhere it is going like this. If you see the top view, so in the inner segment you will see the cross section with a charge of plus Q, and then you will see the cylindrical shell with a charge of minus 2Q. This will be the, and if there would have been any field, I don't know whether the field will be there or not, we have seen in Gauss's law. Had there been any field, it would have been cylindrically symmetric. No other possibilities there. Field would have been cylindrically symmetric. So this would be dA and this is E. Both will be perpendicular to the cylindrical surface. So the first point is that the first part of the problem says we have to find the electric field at all points outside the conducting shell. Outside the conducting shell. So we have to go outside, and when you are going outside, when I'm going outside, the complete charge of the system can be in the Gaussian surface. So when I'm going for first part, outside shell, okay, same, just for the time being I'm taking same. I don't know whether the radii are given or not. No radii are given. So what I'm doing, I'm just assuming some radii. Same, this radius is A, this radius is B, and right now I'm at a point P at a outside point. So for this I'm taking a point P at a distance R. We have to find electric field at a distance R, and R is greater than B. That's why we have to be outside. So the range of R will be greater than B. Okay. So in this case, of course, I can make the whole this thing inside. Okay. This inner cylinder has a charge Q. This outer cylindrical stripper shell has a charge minus 2Q, and I have to find the electric field at a point P. So since there is a cylindrical symmetry, we all know, we have done so many times in basic. I'll make a cylindrical surface. Here it is, I'm making the cross-sectional view. So it is appearing like a circle, but basically it is the top of cylindrical surface, and field would be having cylindrical symmetry. So field would be like this. And your area vector dA will be outward. So we know in cylindrical symmetry we have seen many times dA and E dA and E have the same direction, that is your Gaussian surface, correct? So now let me evaluate the integral. So integral of E dot dA for this Gaussian surface, since it is cylindrically symmetric, E will come out, cos 0 will come out, what is left is dA. So I'll get E 2 pi RL, got it? That is the surface integral of the electric field. Now what is the value of Q in? So the value of Q in, total net charge within the Gaussian surface. So this is Q plus minus 2Q. So answer will be minus Q, correct? So you will have the answer minus Q. Now apply Gauss's law. So you'll get flux is equal to Q in by epsilon naught, and flux is what, integral of E dot dA is equal to what is Q in minus Q by epsilon naught. So you will get E 2 pi RL is minus Q by epsilon naught. So E will come to be what? 1 by 2 pi epsilon naught L multiplied by minus Q into R. So when R is greater than B, you are getting the electric field as, when I'm making the outward model, this I'm getting the field as outward model, remember, because in our model I am making the field outward. So outward field is coming to be minus Q by 2 pi epsilon naught LR. So this is the first part of the problem, when you are outside the whole cylindrical system. Okay, and now see, you can also, suppose the answer can be written as the inward model, because when you made here, and R is the distance from the common axis, correct? Coaxial. So when you have derived this formula, so basically you have made the field outward. And in this derivation, your E came to be minus Q by 2 pi epsilon naught LR. So one way of writing the answer is this. You can write this much field radially outward, correct? You can write this much field radially outward. Okay, but suppose if you want to report your answer as a field in radially inward way, so simply reverse the sign of the source charge. So if you want to write inward and you got outward as negative, so inward would be Q by 2 pi epsilon naught L by R, and this you can write radially inwards. So that depends on you how you like to report the answer. Now let's see the next part. Part B is all points outside, the distribution of the charge on the conducting shell, how the charge will be distributed. Okay, now we have seen the fundamental how the charge get distributed. Remember, since this is conductor, induction will take place. Okay, induction will take place. So inner cylinder has a charge of plus q, and there is no, it is symmetrically located. The inner cylinder is coaxial with the outer envelope. So the induction will take place and a charge of minus q will be distributed uniformly on the inner wall, correct? So inner wall of shell has a charge of what? Minus q, uniformly distributed, correct? And since induction never creates the charge, we know, we have seen all this fundamental. So as soon as minus q appears on the inner wall of the shell, a plus q charge will go to the outer wall. Plus q on outer wall, and already on the outer wall there was a charge of minus 2q. So net charge on outer wall will be what? Minus 2q plus q, that is how much? Minus q. And again, since there is no foundation near the outer wall and your surface is curved with same steepness, so by the property of the distribution of charge, this minus q will be distributed uniformly on outer wall, correct? So this is answer to part B. Okay, now let's come to part C. What will be the electric field in the region between the cylinder? Now you have to find the electric field in the region between the cylinder, this thing. That means we have to find the electric field in the range of R between A and B, correct? Again, had there been any field in between the region of the two cylinder, it would have been cylindrically symmetric. So we will apply the same approach as we applied for part A, correct? We will apply the same approach as we applied for part A. So now I am finding the electric field at a radial distance R when R is between A and B. So first of all, let me make the system. So this is the inner cylinder, this is the outer cylindrical shell of charge. I'm making it a bigger little bit so that, okay, it has a charge of how much? This is conducting and it has a charge of minus q plus q. We have assumed model that has a radius. Of course, your answer will not come in terms of A and B, and I have to find, now take the target point at a point P somewhere in between A and B. So I will make a Gaussian surface. Again, had there been any field, it would be cylindrically symmetric. So I'm making the field. I don't know whether field will be there or not, neither I know it, if it is there, would it be radially away or radially inward. But if there is any possibility of field, it will have cylindrical symmetry. Either the field will not be there or field will be cylindrically symmetric. Now I will make the Gaussian surface. So I'm making a Gaussian surface as a coaxial cylinder passing through P as we did in part A. So this is your Gaussian surface. Again, I am reminding you, these are not circles, these are the top surfaces of cylinders. Okay, now you will find the surface integral. So you know the cylindrical Gaussian surface in cylindrical symmetry has E and dA in the same direction. So I'll get E dot dA is E cos 0 dA. So I'll get E 2 pi RL. Okay, that is the surface integral of the electric field. Now what is the value of Q in? So this only, now this much charge is inside this green Gaussian surface. So Q in is simply Q. Now apply flux is equal to Q in by F epsilon naught by Gauss's law. So I'll get flux is what? Integral E dot dA is Q in by F epsilon naught. So I will have E 2 pi RL is what? Q in is plus Q by epsilon naught. So E will come to be 1 by 2 pi epsilon naught L Q by R. This is the answer. And this answer came when you are making the field as the outward model. So this is the electric field outward. This is the electric field outward where between the cylinders.